This section focuses on better integrating coded compressed sensing and approximate message passing. In some sense, this can be thought of as a natural goal because coded compressed sensing is tailored to sparse recovery in very large dimensions, and AMP can be a very efficient compressed sensing solver. To inform our discussion, we go back to a notional diagram for coded compressed sensing. But this time, we distill it down to elementary concepts. From the top, we have the following progression. First, an information message is encoded using an outer code. The encoded data is then partitioned into small fragments, and within each slot, indexing is employed to select a transmit code word from a codebook. These signals are then added over a multiple access channel, and in the original scheme, a CS solver is applied to every slot to recover a list of transmitted fragments. As a last step, the redundancy contained within the outer code is used to disambiguate messages from the collections of output from the CS solvers. The first modification to coded compressed sensing we wish to discuss is its connection to sparse regression codes and the ability to use approximate message passing, or AMP, as a practical recovery algorithm for the inner code. This contribution is due to Fengler, Jung, and Kare. Let's explore their scheme. One way to view the structure of coded compressed sensing is to think of the slots, after data fragmentation, as independent entities. Specifically, the original sequence of bits is split into L fragments. Through slotting, the multiple access channel then gives rise to L compressed sensing problems, each of a manageable size, say with a matrix width of 2 raised to the 16. However, another way to think about the problem is to aggregate the L index vectors into an L sparse vector of length L times 2 to the 16. From the point of view of a device, this vector conforms to the structure of a sparse regression code. The transmitted signal in coded compressed sensing can then be obtained by multiplying this vector by a block diagonal matrix on the left, where each of the block is equal to the dictionary matrix of the corresponding slot. One of the key insights from these authors is that the complexity reduction in CCS comes not only from the divide and conquer approach applied to the slots, but also from the reduction in the overall matrix width from effectively 2 raised to the 128 to 16 times 2 to the 16. The authors then argue that in the spirit of sparse regression codes, it should be possible to use a full matrix rather than the original block diagonal matrix of CCS. Pragmatically, this is possible because, with the help of fast techniques, we can handle matrices of width 2 raised to the 20. Furthermore, it should be possible to use approximate message passing as a solver for this problem, much like its application to the decoding of sparse regression codes. And indeed, they show that this is possible. Recall that the approximate message passing algorithm can be viewed as a composite scheme that iterates between two equations. At the top, we have the computation of a residual based on our current estimate of the state. At the bottom, we have the computation of an effective observation. The state estimate is then obtained by feeding the effective observation to a denoiser. We note that the residual is enhanced by an Onsager correction, which helps preserve desirable statistical properties and favors convergence. To people familiar with approximate message passing, this should be somewhat straightforward. Yet a suitable denoiser has to be defined for the problem at hand. The denoiser is where we can take advantage of known problem attributes. For instance, in the problem we're currently interested in, we know that every section of the aggregate state vector should be k-sparse. The non-zero entries should also be 1. So we want a denoiser that can take advantage of these properties. A first guess in coming up with a suitable denoiser for this problem may have been to mimic the operation of the M denoiser for sparse regression codes. Unfortunately, because sections of the state vectors are k-sparse rather than 1-sparse, this leads to computational difficulties and it renders this approach impractical. The denoiser put forth by Fengler, June, and Kyrie is a posterior mean estimate that only incorporates the fact that there are k non-zero entries per section through a prior. This leads to a marginal estimator that is tractable and works quite well. It also circumvents the combinatorial issues of having to consider 2 raised to 16 choose k cases per section, which cannot be done in practice. Since the prior queue is static through the iterative process, we call this parameter in the PME an uninformative prior. This denoiser is separable because every entry is computed independently, and it operates section by section. The effective noise variance, tau squared, can be computed through the state evolution equation, or it can be approximated as the normalized version of the energy contained in the residual z at time t. This graph shows the performance of this new access scheme. On the x-axis, we have the number of active devices. On the y-axis, we have the required EB over N naught to achieve a per-user probability of error of 5%. We can see that CCS AMP outperforms the original CCS algorithm when the number of active devices is above 125 or so. Below this point, the two curves are very close. Overall, this is a significant step forward. Next, we explore how it's possible to improve on CCS AMP by leveraging some of the lessons we've seen so far. I should point out that for this particular contribution, we enlisted the help of Cynthia Rush, whose intricate knowledge of AMP was key in resolving some of the challenges we were facing. In Fengler's scheme, the outer code is used for disambiguation at the very end, but it's not integrated into the decoding of the inner code. Yet we know from enhanced CCS that we may obtain significant gains if we find a way to take full advantage of the structure of the outer code during AMP iterations. In CCS, we were able to do that through column pruning. However, for CCS AMP, we face two challenges. First, the AMP algorithm does not take a sequence of hard decisions. Rather, it lets the state vector converge softly over time. As such, column pruning is not an option. Also, if we want to pass soft information around, we have to maintain beliefs over the full length of the sections, say 2 to the 16. Together, these two considerations warrant some new thinking for the outer code. The role of the original outer code in coded compressed sensing is singular. It's supposed to stitch fragments together. Also, the decoder operates over short lists of k fragments, and the location of parity bits offers a trade-off between performance and complexity. For the new code, we have two objectives. We still wanted to be able to perform disambiguation at the end, and on top of that, we wanted to guide the AMP iteration process in the right direction. The basic idea is to use an LDPC outer code and employ belief propagation to provide section estimates within the denoiser. Let's see what this may look like. On this slide, we see a somewhat generic factor graph for the outer code. The variable nodes in the middle correspond to the states of the k-sparse sections. The factor on the right are the constraints of the outer code. The nodes on the left are the local observations afforded by the approximate message passing algorithm. The messages are somewhat standard. Messages from the variable nodes to the factor nodes are the product of the extrinsic belief vectors coming in. Messages from the factor nodes to the variable nodes are obtained by applying the factor rules. However, there are a few subtleties that we will mention briefly. First, there are k-code words living on this factor graph at the same time, as opposed to one. This creates the need for large sections. Second, we do not keep a belief for every possible state within a section. There is 2 raised to 16 choose k such states, and that's simply too large. Rather, we do some approximation where only marginal beliefs on elements are kept, and the belief on a state is taken to be the product of its marginals. Moreover, we need to pass beliefs at a scale of 2 raised to the 16. So we use a code conducive to fast methods like the fast Fourier transform or the fast Walsh-Hadamard transform to do this efficiently. This is partly what the equation at the bottom is supposed to convey. We turn to the design of the outer code. One phenomenon that we have to take into consideration when designing the outer code is mixing. This is a byproduct of having several code words on the same graph at the same time. Suppose, for the sake of argument, that we have 2 information sections and 1 parity section, each of length 4, with 2 non-zero entries per information section. This can lead to 4 parity patterns being equally likely, as seen on this graph. We can take this to much larger section sizes. Suppose that we have k non-zero entries per section. If a parity section is attached to 2 information sections, then there will be k-square highly likely parity patterns. Likewise, if the parity section is attached to 3 information sections, then there would be k-cube highly likely parity patterns, and so on. So, if we have any hope of the outer code providing useful information to the inner AMP decoder, we want factors of low order, say with 3 connections at most. This fact motivated the triadic design shown on this slide for the outer code. We use large section sizes, say 2 to the 16, because we have k non-zero entries per section. We pass beliefs using a fast method, such as the fast Fourier transform or the fast Walsh-Hadamard transform, and we use a low edge count on most of the factor nodes to offer meaningful information to the AMP denoiser within every iteration. Altogether, this is what one of our designs looks like. Again, once we've settled on the structure of the outer code and some approximations, the message passing rules are somewhat standard. We note that belief propagation also gives an estimate about the probability that a particular entry within a section is non-zero. For our implementation, this estimate is given by this expression. This represents the belief that a particular device has a 1 at index location k within section L. This slide summarizes how we use the outer code within one AMP iteration. It remains to explain how this is integrated into the approximate message passing algorithm. As you can see, our implementation of the AMP algorithm is very similar to the one we've seen before, with the computation of the residual at the top and the computation of an effective observation at the bottom. The main difference is hidden in the denoiser. Recall that the denoiser put forth by Fengler, Jung, and Caire is based on the computation of a posterior mean estimate for every entry. We do the same here, except that we substitute the uninformative prior that they were using by a refined estimate obtained through belief propagation on the outer graph. This helps the outer code guide the AMP algorithm in the right direction towards the right solution. The performance gains associated with this latter implementation of CCS AMP are very significant. On the left, we have a graph of the performance. The x-axis is the number of active devices, and the y-axis is the required EB over N naught in dB for per user probability of error of 5%. The gap between the two schemes is very noticeable. On the right, this figure shows the computational complexity. The x-axis is again the number of active devices. The y-axis is empirical runtime. Performing BP as part of the denoiser does take a bit more time, but the difference is somewhat negligible. So this points to an algorithmic improvement with very low overhead in terms of computational complexity. There are several open questions about the CCS AMP architecture. First, what are optimal, or at least good outer codes for integrating coded compressed sensing and approximate message passing? We found one code that seems to work well, but I certainly don't have much of an understanding of how close it is to optimal performance. I'm not even sure how to tackle the simpler task of designing suitable codes when several devices are picking code words from a same codebook. It may also be possible to improve on the CCSM denoiser. In some sense, our scheme and our findings are preliminary. Several challenges and research opportunities remain. I want to conclude this section with an example of a potential improvement that we've discovered recently working with Stefano Rini. One of the challenges with the outer code in CCS AMP is the fact that multiple devices are using the same codebook. Belief propagation is not well equipped to deal with this issue. To circumvent this problem, we can create multiple codebooks and have every device select one of them at random. They can do so based on the first few bits of their information message. This creates some sort of stochastic binning with fewer devices per bucket on average. We can then perform joint demixing across all the buckets using CCS AMP. This is more computationally intense, and we have to estimate the number of devices per bucket. Still, performance seems to increase significantly as we grow the number of buckets. On this figure, the x-axis is EB over N naught in dB, and the y-axis is the per-user probability of error. The horizontal black line is our typical target of 5%. For 64 active devices, we can gain nearly 1 dB by going to 8 buckets. That's very encouraging. Again, this is an instance where there's a natural trade-off between performance and computational complexity. As usual, we conclude this section with a few pertinent references. I hope I've convinced you that coded compressed sensing and its derivatives form an interesting paradigm for sparse support recovery in very large dimensions. These pragmatic algorithms feature reasonable complexity and they offer very good performance. At the same time, there are many interesting open problems related to CCS, especially as a means to enable massive machine-type communications in the future.